So the next big thing for our calculus class is going to be this idea of a Riemann sum. All right. Now what you have right here is the official definition of a Riemann sum. Okay, and it's pretty out there as far as the mathematics are concerned. What all this says right here, and I'll go over it in a second. But let's put it into English first of all. All right, Riemann's idea for these sums is basically 3 steps. The first step is make rectangles. All right, we're looking to get the area under a curve, but we don't have an exact formula for whatever these curves happen to be because they're not rectangles or trapezoids or semicircles or anything like that. These formulas, these functions, they're all over the place. So what do? We keep it simple. Let's make some rectangles underneath the curve. All right. Why do we want to make those rectangles? Because we can find their areas. All right. So after we make the rectangles, find their areas. Okay. And then once you've got all the areas, you're going to add them together. All right. And if you do so, you're going to get an approximate value for the area under the curve. It's not going to be exact, but it will give us an approximation, which is good enough for now. Okay. So what are we doing here with these Riemann sums? We're making rectangles, we're finding their areas, and we're adding these areas up. That's what this is saying right here. All right. We're talking about a function on an closed interval from x equals a to x equals b. Subdivide that interval into n subintervals. Now it could be 4, could be 40, could be 4 million, but whatever n happens to be. All right. So the bases of our rectangles, the lengths of these subintervals, which are the bases of the rectangles, we'll call them delta x1, delta x2, delta x3. We know from science and math class that delta means change. So the first change in x, the second change in x, the third change in x, the last change in x. Okay. During each of these subintervals, you're going to choose an evaluation point. All right. So somewhere, all right, I'm going to go up here. All right. We're going to say that here's x sub 1, x sub 2, x sub 3. So we're going up to our function, and we're touching our rectangle is touching the function at these values. All right. Now, if this is x sub 1, well, then this 4 happens to be f of x sub 1. And if this is x sub 2, then this happens to be f of x sub 2. All right. So we're getting the function's values. The function's values are the heights of our rectangles. All right. So all these right here, all these delta x's, these are our bases. These are these are the points leading to the heights. The heights are actually f of x sub 1. All right. These are the heights. So there we go. This is height times base plus height times base plus yada 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 plus height times base. What's height times base? That's the area of a rectangle. All right. This is what a Riemann sum is doing, getting all of these areas, height times base, and adding it up. Height times base, added up. Height times base, added up. So we're adding up all the areas. Now, Riemann is very general with his definition. Okay, he doesn't say that all of the bases have to be the same size. Okay, some rectangles might be very skinny, some might be rather wide. All right, you'll see that on the exam. Sometimes we have a small interval, sometimes we have a large interval. Okay, sometimes we might have all of the bases be the same number of units. They might all be 2 units. Okay, it doesn't matter as far as Riemann is concerned. Okay, Riemann also didn't care where on the top part of the rectangle it touched the curve. All right, just somewhere in that region we need to have our rectangle touch the curve. That gives us our height. Now, even though there's a variance over where the rectangles can touch the curve, as far as AP Calculus is concerned, we're going to look at 3 spots. The upper left-hand corner of the rectangle, the upper right-hand corner of the rectangle, and the middle of the top side of the rectangle. So here's a visual of what we're talking about here. So here's our graph, okay, and let's just make a function here, a nice simple f of x function, okay. And if it's a left Riemann sum, then that means that the upper left corner of the rectangle is going to touch the curve. All right, so I'm just going to make a couple of these rectangles right here. You can see that sometimes the rectangles are below the curve, sometimes the rectangles are above the curve, but always the upper left-hand corner of the rectangle touches the curve. This is what's known as a left Riemann sum. With a right Riemann sum, now instead of it being the upper left corner, as you can imagine, it's going to be the upper right corner. So here's another function. Doesn't always have to be the same function, but our upper right corner of the rectangle is going to touch the curve. And again, sometimes the rectangles might be skinny, sometimes they might be wide, it doesn't matter, but always the upper right corner of the rectangle is touching the curve. And finally, with the midpoint Riemann sum, now we're talking about the middle of the function, or rather the middle of the rectangle touching the function. So here's a curve right here, and we want the middle of the rectangle. So we'll go the same distance in each direction. We can see that this one is actually going to be the most accurate of the three, because we have some space which is missing and some space which is too much, and some space which is missing and some space which is too much. So they tend to even each other out, which is not always the case with our left and right Riemann sum. So the midpoint, they are the most accurate of the three. But we want to be ready to do Riemann sums for all three of the points. Now, what would be the ideal amount of rectangles? Well, if you haven't figured it out yet, an infinite number of rectangles. All right, we're doing a Riemann sum with 4, like you'll see in example 6. That's great. What's better than 4? 40. What's better than 40? 400. What's better than 400? 400 million. All right, but an infinite amount of rectangles would be the ideal amount. Okay. Now, if we're talking about an infinite amount of rectangles, okay, well, let's think about what a Riemann sum is. All right, remember from the other side. All right, we need the base times height, base times height. So our first height was f of x sub 1, and our first base was delta x sub 1, right? And then our second rectangle, all right, height was f of x sub 2, and base was delta x sub 2. And our third one was f of x sub 3 times delta x sub 3. Okay, so height times base, height times base, height times base. Now, if we want to do this for an infinite amount, we're going on forever and ever and ever. And that's just too much to write. Okay, because we're talking about getting way out here, and we want this to be f of x sub infinity. We can't put infinity right here because the subscript have to be numbers, and infinity is not a number. Right? So from earlier in the year, how do we get around this whole infinity issue? Yeah, if you're thinking to yourself, oh yeah, we did limits as x approaches infinity, that's what's going on here. So we're going to make this the nth rectangle, in other words, the last rectangle. And n has to be a number, all right? Well, so we're going to take the limit as n, which is a number, and what's it approaching? Well, it's approaching infinity, all right? So if we have an infinite number of rectangles right there, this gives us, that's equal to the exact area. Right? So if we want the exact the area, the formula basically is right here. We're doing a Riemann sum with an infinite number of rectangles. Now, that's going to be rather difficult to calculate because we're never ending with the amount of rectangles that we're making. Okay? So we have to look and see how we can calculate it in a different manner. Right? But in the meantime, just keep in mind that right here what you see, this is leading us to something that's known as the definite integral. Because this is an awful lot to write. Okay? We're adding up a whole bunch of products. Right? So mathematicians don't want to write all this out. So instead, they eventually worked out this. We had a sum. So there's our letter S for the sum of and we're going to start at a point A, x equals A. We're going to end at a point x equals B. So we're trying to find the area of the region under the curve from A to B. Well, what are we adding? We're adding height times base, height times base, height times base. So what's our height? Our height is our function. What's our base? Well, the base is this delta x. And delta in our alphabet begins with the letter D. So we have this dx. This is something that's known as the definite integral. Right? And for now, you just worry about its name. We'll talk about it more shortly. But this is the definite integral, and it is equal to a Riemann sum with an infinite number of rectangles, which is the exact area under the curve. This is where we're heading, but before we can head there, let's do some practice with Riemann sums, as you'll see with examples 6 and 7.